Some of the basic definitions involving a basis of a vector space. We will discuss linear combinations, linear independence, and span. Then we'll go over some examples just to remind everyone about these concepts. First, we're going to talk about a linear combination. A linear combination of a set of vectors v1, v2 out to vn is a weighted sum of all the vectors. The idea behind a linear combination can be thought of in two different ways, and each is really a mirror image of the other. First, a linear combination is a way of taking certain vectors and combining them together, with each vector being weighted differently to create a new vector. Another way of thinking of a linear combination is a way of decomposing the vector w into a set of components. So the scalars in the linear combination above, alpha 1, alpha 2, describe how much of w points in the v1 direction, how much points in the v2 direction, and so on. Often these component vectors, v1, v2, are simpler or have some sort of special property. So knowing how any vector can be decomposed into these special vectors is very helpful. As an example, we see here how to decompose the vector 3, 2 into two simpler vectors, each with a different weighting. Note that this is not special to the vector space Rn, but can be done for any vector space, and in particular, for our purposes, a function space. So we can take three functions as vectors in the space of continuous functions, C01, and combine them to create yet another function in C01. The next question to ask is, what type of set should I use to decompose my vectors in some sort of linear combination? There are some natural questions, such as, will I be able to decompose all of my vectors in my vector space into a linear combination of this set of vectors? Or, using this set of vectors, will my decomposition always be unique? Or will there be more than one way to write each vector as a linear combination of this set? And the answer to all these questions leads to the idea of a basis of a vector space. A basis of a vector space is a set of vectors v1, v2, out to vn, with the property that all vectors in V can be written uniquely as a linear combination of the vectors in the basis. This is obviously the perfect type of set for decomposing vectors, since we can decompose all vectors using this basis, and there will only ever be one way to write this decomposition. The number of vectors in a basis is always the same for any given vector space, and this tells us an important property about the space called the dimension. The dimension is essentially the number of degrees of freedom in each vector in the space. Note that a vector space can have many different bases. Some have different properties, some being simple, other being complex, but with a useful property for a particular application. For an example, we have the well-known basis for R3, and we have these three vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, and it's easy to see how any vector in R3 can be written as a linear combination of these three vectors, and there's really only one way to write it as a linear combination of these three vectors. Next, we'll consider the vector space P2. This is the space of all polynomials of degree 2 or less. A typical basis for this space is given by the set 1, x, and x squared. Taking any polynomial in P2, we can see it can be written as c0 plus c1x plus c2x squared, where some of those could be 0. This is our typical formula for a polynomial of degree 2 or less. And this is already a linear combination of the basis vectors in S. And really, this is the only linear combination of these basis vectors that will yield the polynomial P. And finally, we note that by examining this basis, we can say that P2 has dimension 3. As a final example, we're going to look at example 3.27 from the book. This is a different basis for P2 that looks more complicated but has a very useful property that we'll discuss in the next video. It's given by these three polynomials here. We show that any polynomial p in P2 can be written uniquely as a linear combination of these three polynomials. Taking a general p in P2 as seen before, c0 plus c1x plus c2x squared, our goal is to show, and we set it equal to a linear combination of these basis vectors. Our goal is to show that there is a unique value for a0, a1, and a2 for a given p. So by combining like terms and equating the coefficients, we're able to obtain the following three linear equations for a0, a1, and a2. We can show, using linear algebra, that this linear system of equations has a unique solution no matter what p we use, that is, no matter what the values of c0, c1, and c2. Finally, we recall two definitions from linear algebra. First, a set of vectors is called linearly independent if the only scalars satisfying the given equation, c1 v1 plus c2 v2, all the way out to cn vn is equal to 0, are 0. Another way of stating this is that the only way we can have a linear combination of these vectors equaling 0 is if the weights on all those vectors are 0. Next, we have the idea of a span of a set of vectors. And the span of a set of vectors is all the vectors that can be created by a linear combination of those vectors. And with these definitions, we come to the usual idea of a basis, which is a set of vectors that is both linearly independent and span the vector space V.